Hello everyone. Welcome to the collaboration between LIGO India Public Outreach Team and 137 Inverse, which is the Physics Club of IISER Berhampur. So I am Amrita and I have Abhigyan with me. We are the core committee members of 137 Inverse. So in this series of interviews, we are going to speak with eminent gravitational wave scientists who have made major contributions to LIGO and to the gravitational wave science community in India. So the purpose behind this is to popularize the upcoming observing run, that is O4, and to make people aware of this thing and to spread its importance in the scientific community. So today we have Professor P. Ajith from ICTS-TIFR Bangalore. So we'll talk about his exciting journey in the field of gravitational wave astronomy. Welcome, sir.
Thank you.
And so we'll begin, and I'll hand it over to Abhigyan to start with the first question.
Hello, Professor Ajith. You are one of the well-known figures in Indian gravitational wave astronomy. So currently you are a professor at ICTS Bangalore. Could you please tell us how this journey started and how you got interested in this gravitational wave astronomy?
Yeah, I must say that it's not by design, or it happened due to a series of accidents. So when I was a master's student at the Mahatma Gandhi University in Kottayam, during one summer, I had applied for sort of a summer program of the Indian Academy of Sciences, and my intention was to work on a field that is very different from astrophysics, more like statistical physics and condensed matter. And a very famous Indian scientist has sort of agreed to take me also. But at the end, I did not get selected for this program. Then I asked my teachers, if there is any backup option. And two of my professors, Professor Indulekha and Professor Vijay Govindan, actually wrote to one of the fathers of Indian gravitational wave physics, Professor Sanjeev Dhurandhar at IUCA, whether he could take me as a summer student, and he graciously agreed. That was my first exposure to gravitational wave astronomy and gravitational wave physics. And I remember my project was to rederive this calculation, this very famous paper by Peters and Matthews, which calculates the gravitational waves from an inspiraling compact binary using a leading order calculation in general relativity. And that really liked it, and that's sort of how I was introduced to the field of gravitational waves. And the next year, I worked with another doyen of Indian gravitational wave physics, Professor Bala Iyer, and kind of stuck into this field. So in some sense, it's some random perturbation that happened at some point. You can see it's not very different from what happens in physics or cosmology also, right? For example, the fact that we are here in this galaxy living as human beings is due to some random perturbation that happened billions of years ago. But then if that sort of excites you, and if you're able to pursue that, you put some hard work, etc., there is sometimes with some luck, some exciting journeys are possible.
So it started with your interest to do statistical physics, and now it's going on with gravitational waves.
Yes.
Okay. So we understand that your primary work, as you have already mentioned, is focused on gravitational wave astronomy now. So your website mentions that you model the gravitational wave sources then by using analytical and numerical relativity. You do data analysis and interpretation of the observations. So that is what your website tells about your research, and we'll speak about each of these in more details in the other questions. But if we ask you to brief your work, what would that be, like very short?
Yeah, my work also has sort of gradually evolved over time. In my PhD in Germany, I started working very closely with an actual gravitational wave detector, a much smaller one called GEO600. And the projects I was involved in was, for example, how do you distinguish between real gravitational waves and fake noise transients that look like gravitational waves. It's an important problem even now, because that really determines our ability to discover real gravitational waves, because you need to distinguish between what is true gravitational waves and what is a fake signal. But in 2005, around that time, a big breakthrough in numerical relativity happened. Numerical relativity is basically a field that basically aims to model gravitational wave sources using supercomputers, because these gravitational waves are generated by objects like compact binary systems of black holes or neutron stars, and they are in a regime of extreme gravity, and these objects move with extreme velocities. And if you want to model the dynamics as well as the gravitational waves from these inspiraling or coalescing binaries of black holes or neutron stars, you have to solve what are called the Einstein's equations, which are the basic equations of Einstein's theory of gravity, the general theory of relativity. And these equations are notoriously hard to solve for realistic systems involving multiple objects, multiple black holes that are moving, etc. And we have, for example, last 4 decades or so, there has been systematic work by a series of scientists to develop approximation methods, like what is called a post-Newtonian approximation, to solve these equations and compute the gravitational wave signals when these objects are at large separations, when they move at small velocities, and when the gravitational fields that they face are reasonably small, etc. But eventually, if these objects move around each other, they emit gravitational waves. They come closer and closer in a process called in-spiral. There's a spiral inwards. And eventually they would move with very large velocities close to the speed of light, and then would merge. And at this time, you cannot use these approximation methods, because the assumption used in the approximation methods, like these objects are moving in slow velocities, they are observing in small velocities, etc., and they're observing small gravitational fields, etc., are no longer valid. So and these numerical relativity basically try to solve these Einstein's equations exactly using large supercomputers. There has been a large amount of work, but the first successful simulations happened in around 2005 when I was a graduate student, and I got interested in this exciting field, and I started collaborating with people who do this numerical relativity simulations to create semi-analytical models of the gravitational wave signals that we can use in LIGO to search for such signals that we expect in the data. And one cannot use these numerical simulations very often, because they are very expensive. So you can only have a small number of numerical simulations, but in an actual LIGO data analysis, you need millions of model waveforms or template waveforms that cover the region of interest that we want to search for, covering a spectrum of black hole masses, etc., etc. So my first I branched out into modeling gravitational wave signals by combining analytical and numerical relativity, and we worked on this method called phenomenological method, which is still used in LIGO and Virgo to model gravitational waves, to search for them, etc. And I also looked at the implications of these things. For example, how you actually use these models to design a search for gravitational waves from binary black holes, because it requires a number of technical challenges, creating template banks, performing searches, dealing with false alarms, etc. So with several collaborators, we worked on a series of research program that basically was helpful in implementing these numerical relativity inspired waveforms in LIGO data analysis. And these such waveforms are now used in the LIGO data analysis routinely. And the second, after moving back to India, joining ICTS, I started switching to more on the observational aspect, because the gravitational wave detection was imminent, hopefully. And we developed with other colleagues, younger colleagues at ICTS, we developed a test of Einstein's theory using gravitational wave observations. And the idea here is that if you have a binary black hole merger, you have a long in-spiral followed by the collision of these black holes, the merger, and it forms a new black hole that oscillates, producing what is called the quasi-normal modes. And if you have a signal that covers this entire spectrum of frequencies, then you can first look at the part of the signal that is produced by the in-spiral of these black holes and measure their properties, like the masses of the black holes producing this gravitational waves, etc. And using these numerical relativity simulations, you can predict the mass and the spin angular momentum of the black hole, the remnant black hole this merger would produce. One could make a prediction without actually looking at the data, purely using theoretical models of, which is the Einstein's theory. Then you can look at also the part of the signal that is produced by these quasi-normal mode oscillations, or the post-merger oscillations of the binary, and estimate the properties of this final black hole purely from that post-in-spiral part. And if our understanding of gravity is correct, if Einstein's theory is the correct theory of gravity, these two independent estimates have to be consistent with each other. So this will be a test of general theory of relativity. And this was one of the first tests that we used to establish the consistency of this first binary black hole observation by LIGO to the prediction of Einstein's theory. And recently, we have been getting more interested in the astrophysical aspects, because now we are, in the last 5 years or so, LIGO and Virgo have detected order 100 gravitational wave signals from different compact binary coalescences involving black holes and neutron stars. So we are building up, this as a way of understanding the astrophysics. And one particular phenomena that we are interested in recently, I'm particularly excited about, is the gravitational lensing of gravitational waves. So most of you know about the gravitational lensing of light. Gravity bends light, and in extreme situations, you can see multiple images of a background galaxy, etc. It turns out that the same phenomena exist in gravitational waves also. Gravity bends gravitational waves also. So if there is some intervening object, like a galaxy, between a source of gravitational waves and us, this galaxy would bend the space-time around it, and the gravitational waves would propagate in this curved space-time that is curved by this galaxy, this lensing galaxy. Then you could potentially see multiple images of the same gravitational wave source, or multiple copies of the same signal, etc. So just like the gravitational lensing of light has become a powerful tool for probing cosmology, fundamental physics, astrophysics, etc., there is a possibility that gravitational bending or gravitational lensing of gravitational waves would offer a similar tool for astronomical observations. And we are really in the verge of observing the first signatures of the gravitational lensing of gravitational waves. That will happen in the next few years. And a lot of my research these days is focused on this really new, exciting area.
So yeah, as you told, this requires a lot of data analysis of LIGO datasets and all. Can you please tell us in layman terms, what do you specifically search in the dataset? Like after a particular run of the LIGO, there is a dataset regarding the gravitational waves. What is the particular object, or what is the particular signature we will try to do search in LIGO dataset?
So basically, gravitational wave detectors look for disturbances in the space-time as a propagation of gravitational waves. In particular, they look at how the arms of these interferometers change as a function of time. So you basically record a time series data, which can be calibrated to give a amplitude or a strain of the gravitational waves produced on the space that we live here. So the LIGO, the primary data is a time series data from multiple detectors. And this data is dominated by various kinds of noise. There are all kinds of noise sources that affect the sensitivity of detectors, like seismic noise, the fact that we have only a finite number of photons, like the photon shot noise, etc., and also the thermal noise on the mirrors, etc. So there's a large number of fundamental noises that limit our ability to measure. There is also all kinds of technical and transient noises that would create some sort of transient excess power in the data also. But in this data, this noisy data, there could be some signals also. And depending on the sensitivity of detectors, the number of signals will be large or small. And there are different working groups in the LIGO Virgo Kagra collaboration that look for various kinds of signals. The most promising kinds of signals is the signals produced by the coalescing compact binaries of neutron stars or black holes. And they seem to be the most ubiquitous in the universe. They are the loudest sources of gravitational waves. And so far, we have detected the gravitational waves from only these ones. And the nice thing about these kind of signals is that there is a very nice way of modeling the expected gravitational signals by solving Einstein's equations using the methods that I described previously. So you have accurate models of the expected signals. But of course, the shape of these models, we know how this shape of the waveforms look like as a function of time. But of course, depending on the property of the source, like the masses of the black hole, etc., the shape of the signal would change. And since we do not know what kind of signals are there in the data, we have to search for a whole lot of them. Now, close to 1 million such model has to be compared against the data. And the most powerful method for comparing the data with theoretical models is what is called the match filter, which has a lot of, which is invented by radio engineers in the 20th century. But our Indian scientists, in particular, Sanjeev Dhurandhar, B.S. Prakash, etc., have done pioneering contributions to developing or adapting these techniques to the search for gravitational waves. So that's a most powerful way of searching for gravitational waves, in particular, these well-modeled signals like the compact binaries. Now, there are other kinds of sources also potentially. One is the rapidly spinning neutron stars in the galaxy. So we know that these neutron stars exist. And if they are sufficiently deformed, they would produce gravitational waves, which are potentially detectable. But we do not know how deformed they are. So we have some uncertainty on the loudness of the gravitational waves also. So there are, but similar match filter-based searches used for looking for these continuous gravitational waves produced by the neutron stars in our galaxy, rotating neutron stars in our galaxy. Now, there are other kinds of transient sources like, for example, collapse of stars producing supernovae. If a supernova happens in our galaxy, that produces a short-lived excess power, a burst of gravitational waves, which you can detect in the data. And it requires different kinds of techniques. Basically, you look for some short-lived excess power in the data, which is consistent across multiple detectors, consistent across some sky direction, etc. So that's another way of detecting for these excess power bursts like supernovae explosions. There is a fourth kind of source, they're called stochastic gravitational waves. And here the gravitational waves, as the name suggests, look like noise. They are stochastic. There is not a well-defined model for them. But the difference is that they are correlated across multiple detectors. So you cross-correlate the data from multiple detectors to see if there is a correlated noise-like signal in the data. And these could be produced by very energetic processes in the early universe, or it could be also produced by the superposition of a large number of astrophysical sources. So we expect all kinds of different sources, model sources like compact binaries or continuous waves, burst sources like supernovae, as well as stochastic sources. And there are searches going on to detect all these different kinds of sources also. There are different working groups in the LIGO Virgo Kagra collaboration that specializes on all these different types of sources.
So in any LIGO dataset, like there are lots of noise also. I mean, within the noise there is this signal hidden. So exactly how does LIGO try to reduce the noise in each run, or how you, while analyzing the data, try to mitigate the noise and try to find out the original signal?
Yeah, so indeed, the noise is what limits our ability to distinguish, identify signals in the data. And the noises, in some sense, you cannot model the particular realization of the noise. So the only thing that you can do is to minimize the RMS of the noise, and that the power of the noise, and that requires a lot of ingenious engineering and fundamental physics. And for example, if you want to think of, there are multiple fundamental sources of noise. At low frequencies, the LIGO Virgo noise is dominated by the seismic vibrations of the Earth. And to minimize the coupling of the seismic vibrations to the interferometer, there's a very sophisticated isolation mechanisms. So the LIGO, all these subsystems of LIGO, like the mirrors that are used as test masses and the interferometer, etc., are suspended as pendulums of multiple levels. So this has a nice way of isolating the effect. In the effect of seismic noise is suppressed to a very large order at low frequencies. Similarly, there are thermal noise, noise. The fact that these materials are at a finite temperature, the atoms in the mirrors would vibrate, and these mirrors have their own mechanical modes, etc. And to minimize that, you use extremely high quality optics, and also to minimize these the spread of the noise across frequency. You try to narrow this into some very narrow frequency bands, which could be dominated by noise, but here so the other frequencies are sort of less affected by this thermal noise. Similarly, the high frequency is limited by the fact that you have only a finite number of photons that you use in the laser to do interferometry. And here the idea is to use the simple idea would be just to increase the laser power and use more photons to do measurement. But it has other consequences, because if you increase the number of photons, it also increases the fluctuations in what is called the radiation pressure. Basically, light would push these mirrors, and the number of fluctuations, the number of photons would introduce a noise. It introduces fluctuations in the position of these mirrors. So, and to minimize this effect, one uses some heavy mirrors, and for example, the LIGO mirrors are 40 kilograms of fused silica. So so that the same forces applied, the acceleration is sort of minimized because of the large mass. And again, one uses a lot of quantum technologies to improve sensitivity of the detector at a certain frequency band. So these are a lot of very sophisticated instrumentation that is going to building interferometers like LIGO, Virgo, and Kagra. On top of that, we try to minimize, try to develop sort of optimal techniques to detect signals in noisy data. For example, if you have a model of the noise, it would significantly improve our ability to detect those signals buried in the data. It's like, if you know what you're looking for, it's easy to find it. It's similar to, for example, even if you are in a crowd, if someone is speaking your mother tongue, your language, you can easily identify it because you have a library of those words in your brain, right? In the similar way, if you have a library of waveforms of signals, you have a better ability to identify these waveforms in the data. That's essentially the technique of match filtering. But not always we have such luxury, and then we use the next best thing, like the excess power or cross correlation between multiple detectors, etc. But ultimately, all statements that we are making are limited by the noise. So you have a certain confidence with which we can say whether a signal is a true gravitational wave or not. So there is a way of estimating what is your false alarm probability, what is the probability that you are wrong. And there is a robust way of doing it using coincidences between multiple detectors, etc. So, for example, the very first event, we did a lot of work, the collaboration did a lot of work to establish that the probability of a false alarm, this being a false alarm, is extremely small, less than 1 part in a few million. So we have this extreme high confidence in the first few detections. But once we know that the gravitational wave signals are a ubiquitous event, the mergers are a ubiquitous event, you can reduce your requirement on the confidence. And that usually happens in any, in discoveries of physics. The first discovery has to be what is called a 5 sigma discovery. Your probability of false alarm is very small. But once you establish that these are common phenomena, we don't worry too much about how you can sort of lower your threshold on the false alarm probability, but still you need to be sufficiently, that it has to be sufficiently high, or the false alarm probability has to be sufficiently low, so the significance of these events are sufficiently high. So there are different ways of characterizing this significance of the gravitational wave events discovered by LIGO Virgo and now in Kagra and hopefully in LIGO India later.
Okay, so let's turn our attention to O3. So the O3 had produced some very nice results related to the gravitational wave observations, and even you were involved in it. So can you please speak about your contributions to O3?
Yeah, so our group is involved primarily in 2 different aspects of the gravitational wave astronomy. And one is using the LIGO Virgo data to test the predictions of Einstein's theory of general relativity. So one is, we have this particular method of checking the consistency between the in spiral and the post in spiral parts of the signal. we have been, we have led this analysis in the LIGO O4 test of GR subgroup, contribute to this analysis, and that is one of the analysis that I used to establish the consistency of these LIGO O4 events to the predictions of general relativity. And by combining the results from multiple observations, we can significantly improve the constraints on possible deviations from the predictions of Einstein's theory. So in science, we can never prove something. We can, in observational, using observations, you can only disprove things. So, currently we can see that the data is totally consistent with Einstein's theory, and the scope of deviations from my prediction of Einstein's theory is getting narrower and narrower. So this analysis called the in-spiral merger ring down consistency test that our group has developed is one of these means of establishing the consistency. And another activity that our group is contributing to the LIGO Kagra collaboration is the searches for gravitational lensing of gravitational waves. So one has to, now that there is some reasonable probability of observing the gravitational lensing of gravitational waves, we have to develop methods to search for them, to search for signatures of them, and perform these searches. And LIGO collaboration has published papers that summarize the searches for the lensing signatures in the LIGO events. And our group has contributed multiple analysis that looks for the signatures of the gravitational lensing. We were not successful yet. So far, there is no evidence of gravitational lensing of gravitational waves in the LIGO data yet, conclusive evidence. But as we improve the number of detections, increase the number of detections, this chances become non-trivial. We are expecting to observe these first observations of the lensed gravitational waves in a matter of few years.
So what do you expect from the upcoming run, this O4? Like what physical aspects you researchers will be focusing on in this run? And like what things do you want to specifically find in this particular run? Like I can understand that there is one of these aspects is this finding gravitationally bent, this gravitational waves, gravitationally lensed.
Lensing.
So, yeah.
So one nice thing about gravitational detectors is that even with modest improvement sensitivity, the number of signals that you would detect would significantly increase. So for example, O4 would only, in O4, the detector's sensitivity would only by a very modest amount, by a factor of 2 to 3. But because that will give us a large, the number of sources that we detect roughly goes as a cube of the sensitivity improvement. So the number of sources we would detect would significantly increase. So far, for example, in all the last 3 observing runs, we have detected order 100 gravitational signals. But in the next 1 year, with the O4 data, we will be detecting a few hundred gravitational events. This we know confidently because we know the rate of the mergers happening in the universe by looking at the past data, and we know how the detectors are improving, so that we can confidently say that we will be detecting a few hundred gravitational wave mergers in the next few years in O4 itself. Apart from these sort of guaranteed detections, there could be some surprises also, like one might be detecting the stochastic background of the gravitational waves produced by all the astrophysical mergers. A surprising galactic supernova could happen, then we will be able to detect them. One might be able to detect spinning neutron stars and so on. So looking at additional things which are less guaranteed, but there are possibilities of these ones. Our group is primarily excited these days about constraining now departures from Einstein's theory by combining data from more and more events. That's one thing. These could give us 2 results. One is that we would see that Einstein's theory is consistent with better and better significance, or the possible departures from Einstein's theory is less and less. Or one could detect some surprising phenomenon or object. We believe that all these black holes are currently, we expect all these massive compact objects that we detect are black holes, but there is a possibility that there could be something more exotic, and it might show up, but I would not put all my money in betting that. However, there are much more astrophysically interesting situations, which is much more likely to happen, which is, for example, the first observation of the lensed gravitational waves. Again, there are uncertainties on the event rate of these, or the probabilities of these gravitational lensing observations. But we are slowly entering into a regime where detections are possible. So if nature is very kind to us, we might observe a gravitationally lensed gravitational wave in O4 itself. But even in the pessimistic case, it could be we may wait for a few more years. So if you ask me, what are the activities that we are particularly interested in O4 data? One is sort of, again, continuing the tests of gravitational waves, looking for evidence of black hole horizons or the absence of them, and in particular searches for lensing signatures of gravitational waves.
Okay, so this was all about LIGO and Virgo, and so the final question we'll like to discuss with you is about the contribution of LIGO India that is being set up. So what do you think LIGO India can bring into the gravitational wave community, like the importance of this big thing?
Yeah. So one could think of this in multiple levels. One is that always gravitational wave astronomy requires multiple detectors, right? Because unlike an optical telescope, you cannot point a gravitational observatory to a particular location in the sky. It is sensitive to practically gravitational waves coming from practically all directions in the sky. And it's a good thing because you're using a small number of detectors, you can basically cover the whole sky. But the downside is that you're unable to locate the arrival direction of the gravitational waves, which is quite important if you want to understand the source, if you want to follow it with multiple observations like multi-messenger observations, etc. That's where you need to have multiple detectors. The way we localize the sources of gravitational waves in the sky is by combining data from multiple geographically separated detectors. So essentially, it's like you're creating a synthetic telescope that is comparable to the size of the Earth, similar to, for example, what radio astronomers do using what is called a very long baseline interferometry, VLBI, using this event horizon telescope, like etc. So we are doing something very similar, but totally in software. And the larger the number of detectors are, better is your ability to localize sources in the sky. And in particular, if you look at the location of the current detectors like LIGO, Virgo, and the upcoming Kagra, they're all in the northern hemisphere, very far in the northern hemisphere. So they form a particular plane. So you have a good ability to localize sources coming from certain directions in the sky, but not from some other directions in the sky. And luckily, India is very close to the equator. And if you have a detector in the Indian subcontinent, that would significantly improve the localization of gravitational waves all over the sky. So that's a primary contribution that LIGO India will have to the international network of gravitational wave observatories. It will significantly improve our ability to localize gravitational wave sources. This is very important because if you want to now follow up these sources using electromagnetic observations, you need to point these electromagnetic telescopes to that location in the sky. And it's very important to identify that with good accuracy. That's a major contribution. LIGO India will also improve our ability to understand the polarization states of gravitational waves, because you're measuring different combinations of these polarizations. It's a technical detail, but it improves our ability to measure the polarization of gravitational waves and even to test Einstein's theory in that way, because Einstein's theory predicts that gravitational waves, just like electromagnetic waves, have only two polarization states, while there are other theories of gravity that predicts extra polarization states. And LIGO India would be a significant contributor to that measuring of the polarization modes. And if these are the sort of scientific aspect of the contribution of LIGO India, but also there's an equally important technological contribution, because as I said earlier, building a gravitational wave observatory comparable to LIGO and Virgo involves a lot of very sophisticated techniques in fundamental physics, quantum physics, laser physics, optics, mechanical isolation, engineering, control systems, and computing. It covers a variety of frontiers in fundamental physics, applied physics, and engineering. So this is the kind of technology, and this has a lot of technological implication also, and it's an area that we would gain a lot if you are able to develop this expertise in India. So in some sense, this collaboration with LIGO USA is providing us really a shortcut to reach out to the frontiers in the development aspect of that. So that's another very important aspect that the LIGO India project would contribute, apart from the science.
So yeah, we have come to the end of our interview. We would like to thank you, sir, for your time and making us all aware of your field and research, especially regarding this gravitational wave astronomy and its impacts. Hope our audience like it and get inspired to take up GW astronomy as a career option, and hope India flourish more in this field.
Thank you.
With the building of new detector. Yeah. Thank you, sir.
Thank you.